viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani, Department of Computer Science, Aryabat College, University of Delhi. So in our previous lecture we looked into union find data structure. The first part of the lecture was dedicated to this data structure along with the kind of understanding the structure, the application, the usage area as well as the operations also, and we have also seen one example in kind of in a very brief manner. So today we are going to take this topic further, which is union find data structure. We will be looking into one example which is maintained here with the help of arrays, and then we will be kind of going into the algorithmic nuances of the data structure. So let us say I am having a set of elements which is denoted by S, and the elements here are starting from 0 to n. So total n elements are available. So the value of elements or the value or number of the elements is 10. Now what do we actually want to do? We want to the task is to manage the connectivity of elements, and obviously we are going to use a union find data structure for this. Now let me help you recall that there were kind of some functions which are or some operations which can be done on these union find data structures. One is make set x, that is to take the element, only a single element, and make a disjoint set of that. Then you have union x comma y, that means to whichever element your x is belonging and to whichever set your x is belonging, and to set the set to which your y is belonging, combine them and generate one particular representative, and this was union find. And then there was an operation which is there to check whether the elements belong to the same set or not, and the strategy for this is to we can say to find the representative of the set of the element 1, let us say that is x, and then we will find the representative of the element 2, let us say, and if this is say x, that means 1 and 2 are having one particular they are belonging to a same set. Now here let us try to manage this whole thing with the help of an array ARR, and the basic task is to manage the connectivity of elements. Now array, as you all are aware, index must be there. ARR here is indexed by the elements of the set having the size of n. Obviously as there are n elements in set, n is going to be the size of the array, and all those operations which we talk about, which are make set, then union find, and then finding a particular representative, can be used, can be managed, and this array can be used to manage all these operations. Now how? Let us see. So we are assuming that there is an assumption in this implementation. We are assuming A and B objects are connected only if ARR of A is equals to ARR of B. Now how this ARR of A is equals going to be ARR of B, I will show you with the help of an example. Next operation is find A comma B, that is checking if ARR A is equals to ARR B or not. Then there is next operation which says union A comma B. This union A comma B is going to connect A to B and merge the components, whatever is there in A and whatever is there in that set to which B is belonging, and the value after the union is going to be the value of A and B both. Now let us say initially I am assuming that there are 10 different subsets starting from 0 to 9, as we have seen this in the form of an array, and each subset has a single element in it. So this is what your make set operation is. So make set operation says different create different subsets which are obviously disjoint, and initially they have the single element. So that single element is the only element in the subset, as well as the array as well as the representative element of that subset as well. Now here, as you can see in this figure, so each subset contains only one single element. So here we have index and the element, presently it is same. So the arrays ARR 0 is 0, ARR 1 is 1, and whatever the index is, that is the value of the element. So that means all these 10 make set operations have been implemented, and all these elements starting from 0 to 9 are now in the form of different subsets, which are obviously disjoint. Looking into the values, we can clearly make that out, and the make set operation is, let us say, done. Now assuming we take it forward and let us perform some more operations of union and find set and so on and so forth. So let us say we are finding or we are performing an operation which is union 2, 1. That means we are going to join, the version is very simple, we are going to join 1 and 2. But what you need to update in case of this array is, here you can see that now the element at the index 1 is 1, which is the representative element, and element at index 2 is also 1. So that means now the element 1 and 2 are joined together, and 1 is the representative of this particular set. Initially each and every element was in the form of a singleton set, which is a single element set, and they were the members of their themselves, the set containing themselves, they were the representative of the set in which they were lying. Now here from this figure you can make out that 1 and 2 are now lying in the same set, and the representative element or the root element, we can say, is 1 for both of them. Moving further, let us perform union 4, 3. So union 4, 3 is going to give a link between 4 and 3, and let us say the representative element we are keeping as 3. So by convention, let's make out a convention here that a smaller element will be the representative of the set. So when we say 4, 3, so 3 is the representative. Now we are combining, the next step says union 8, 4. So whatever set which is having 4 will be merged or will be union with the element with the subset which is having 8 as its element. So this is going to give a connectivity or an edge, I can say, between the elements 4 and 8. Similarly, if we proceed with the next step, which is union 9, 3. So union 9, 3 is going to give me an edge or a connectivity or a link between 3 and 9. So now the array which will look differently from the previous one is, so for 0 the representative is 0, for 1 the representative is 1, for 2 also the representative is 1, for 3 the representative is 3 of course, for 4 the representative is 3, because now 3, 4, 8 and 9 are belonging to the same set whose representative is the smallest element as per the convention, which is 3 here. So 5 is belonging to 5, 6 is belonging to 6, 7 is belonging to 7, 8 is belonging to a set which is having 3 as its representative, and 9 is belonging to a set which is also having 3 as its representative. So you can check within the figure that there are 3 different colors of the which are showing the representative elements of 4, 8 and 9, and now the new representative element is 3, because all these sets, all these singleton sets of 3, 4, 8 and 9 are combined. Moving further, let us say we say union 6 and 5. So by the convention we are going in the same manner, that the smallest element is going to be the representative. So here 5 and 6, now they have a link in between, and the array will look like this. So, with all the kind of changes which have taken place already, now here is a new change that the representative element of 6 is now 5. So, 6 has been given or 6 has been merged in a new we can say set, and the representative element of that set is 5. Moving forward, we have performed some operations of union A comma B, and now if you notice within this we have 5 subsets. So, one is the subset which is a singleton set 0, another one is the subset which is having 2 elements 1 and 2, representative element of this is 1. Then we have the set comprising of 3, 4, 8 and 9, and the representative element of this is 3. The fourth set here in the list is having 2 elements 5 and 6, and the representative element is 5, and the fifth set is having 7 as the only element, and as it is the only element, the representative element is also 7. So, first set with 3, 4, 8, 9 in order of in which then second has 1 and 2, third has 5 and 6, fourth has 0 and the fifth has 7. And all these components now can be called as the connected components of any graph or something of that sort. Now, you can relate these elements to the node of the graph if the agenda or if the application which we are dealing with is having graphs, and the elements in one subset can be considered as the nodes of the graph which are connected to each other directly or indirectly. And what is the meaning of directly or indirectly? That we have seen in our previous lecture with the help of that friend example. Therefore, each subset can be considered as a connected component. So, element in one subset are considered as nodes of the graph connected to each other somehow, and each subset now can be considered as the connected component. Now, from this, when we talk about these connected components and all those kinds of things, we can infer that union find data structure is a very useful data structure in graphs for performing various operations which are which are related to connectivity, like connecting the nodes. That is going to be simple, it is just a kind of union operation here in case of union find data structures. Or even if we want to find the whether two given components are connected or not, we will be looking into the representative elements. If they share their representative elements, then they are connected. If they do not share it, then they are not connected. So, this makes our life simpler in terms of connectivity operations of your graphs. Now, let us perform some find A comma B operations. So, find A comma B is going to give you result as true if A and B belongs to the same set, false otherwise. So, when I am saying find 0 comma 7 with this previous with this example, so now this is the final we can say the structure of the array which you can see, and now I am looking for find 0 comma 7. So, basically this is asking a question that whether 0 and 7 belongs to the same component, yes or no. So, this is going to give us false because 0 is belonging to the set whose representative is 0 and 7 is belonging to the set whose representative is 7. So, ultimately we can say that both of the elements are belonging to different components, and hence the false is the result. But if we run this query which is find 8 comma 9 for your the elements 8 and 9. So, although 8 and 9 we can say are not connected directly because there is no direct edge between 8 and 9, 9 is connected to 3 and your 8 is connected to 4 and 4 is ultimately connected to 3. But there exists a path connecting 8 and 9. So, it will give us the true true as the result, because find 8 and 9 will actually find that the set to which 8 is belonging and the set to which 9 is belonging, these two sets are same or not. So, these two sets are same, so that means this is going to give us the results true. Now, union A comma B, I have already told you that you need to replace the components containing two objects A and B with their union. Why this replacement is important? As we have seen that we need to maintain the condition of the sets being disjoint. If we are not going to replace the components A and B and we are going to put one more component which is union of A and B, this is going to give us the repetition of the elements of A and B, and hence the disjoint condition of being disjoint is going to be violated. Then find A comma B, it is checking if two objects are in the same component or not. So, if we perform, let us say within that set, if we perform unions 5 comma 2 on the above components, then it will be 1, 2, 5 and 6 in one component, 7 is a different component, so is 0 is a different component, and that 3, 4, 8 and 9 are kind of having one single component. So, now instead of 5, because we have performed one more union, we now have 4 subset. So, we have seen various operations, and this is going to be the final kind of, we can say, status of array in which your components are going to be connected. Now, here you can see that the 5 and 6, earlier they were having 5 as their representative and 2 was having 1 as their representative. Now, by that convention, that smallest number is going to be the representative. Now, 5 and 6 when combined with 1 and 2, 1 being the smallest element will be the representative of the set, and hence here you can witness in the figure that 5 has changed its representative to 1, and so as 6 has also changed its representative to 1 as well. Now, moving forward, as I have told you that we are going to use this union find data structure in kind of in order to determine the connected components, and I have also given you the disclaimer that these kind of tasks can also be performed with the help of DFS kind of thing. So, connected components, if we look for a particular graph, so this algorithm goes like this. So, for each vertex V belonging to the vertex set of graph, we are going to make set V. So, that means all the individual vertices will now form one particular they have their own set by the virtue of this make set V, and for each edge u comma v which is belonging to the edge set. So, a vertex is a combination of edge a graph is a combination of vertices and edges. So, for each edge u comma v belongings to the edge set of E, if find set u not equals to find set v, that means they both belongs to the separate we can say set, then only we are going to kind of say union u comma v, and by this whole scenario we will be able to find the or we will be able to generate the connected components of G, because individually all sets will be determined, and for each and every edge, if they do not belong to, if the two ends of the set are not belonging to one particular edge, the one particular set, that means they are not connected, then we are going to give a union, we are going to perform a union u comma v. Similarly, moving further, if we want to determine the same component u comma v. So, same component says whether u and v belongs to the same component. So, this is again kind of a simple operation which says if find set of u is equals to find set of v, then this is going to return true. That means the component to which u and v are belonging, or the set to which u and v are belonging is same, then true, else return false. So, find set u is going to find the representative of the set to which u is belonging. Find set v is also going to find the representative set to which v is belonging, and if it is same, it will return true, else it will return false. Now, we have seen that this is going to be used in case of some connected components of a graph. But if we look into kind of more detail, one of the very prominent application scenarios of this disjoint set data structure or this union find data structure is Kruskal's algorithm. Now, let me help you recall that Kruskal's algorithm is a greedy algorithm which is used to find the minimum spanning tree MST of a connected, undirected, weighted graph, and this is done by iteratively adding edges with the smallest weights that do not create the cycle. So, Kruskal's algorithm is is a prominent example in which we are going to use these union find data structure. So, Kruskal's algorithm, it is a greedy algorithm. The application is to find, the task is to find minimum spanning tree, and in order to find the minimum spanning tree we can also use Prim's algorithm, but here the agenda is to showcase the usage of union find data structure. So, we will focus on Kruskal's algorithm, and the graph here is going to be a connected graph obviously. Then undirected, it should be an undirected graph because this union find data structure is going to work with undirected graph, and the graph is weighted because minimum spanning tree we are going to find out. So, what is the idea or the basic principle is iteratively keep on adding edge to the tree. These edge should have smallest weights and they should not create cycle. So, agenda is to find the minimum spanning tree, and Kruskal's algorithm will identify a subset of edges that connects all the vertices in the graph, then it is going to be a tree with the minimum total edge weight without forming any cycle. So, if you are going to introduce cycle, it will not remain a tree, and minimum total edge weight is required because we are looking for minimum spanning tree. So, why do we call this Kruskal's algorithm as a greedy approach? Simply because this this algorithm implies a greedy technique or a greedy choice, that it works by repeatedly selecting the edge with the smallest weight that does not create in the cycle in the current spanning tree. So, we keep on populating the tree, we keep on adding the edges into that tree. The only condition is the weight of the edge which is going to be added should be the smallest among all, and it should not create a cycle. Now, please think that how are we going to use this disjoint set data structure into this whole nuances of Kruskal's algorithm. So, disjoint set data structure, as you already know, that it uses a disjoint set data, Kruskal's algorithm uses a disjoint set data structure to efficiently track which vertices are connected and to detect the cycle. So, the condition is cycle should not be formed. So, cycle should not be formed, that means the vertices which we are going to connect newly should not have the same representative. If the same representative is there, that means they are already connected, and if connected again with a different part, they will definitely create a cycle. So, disjoint set data structure or union find data structures we generally employ for this thing. So, if we summarize this lecture, we have seen what is the process, we have seen the details of all the algorithms, we have all the operations which are the make set operation, union find, and finding the representative elements. Then we have also seen the utility of this disjoint set data structure or union find data structures, that where they are actually going to be used if we talk about Kruskal's algorithm. We will be taking Kruskal's algorithm in the light of this union find data structure into more detail in our upcoming lecture. Here is a list of references which is being used for the preparation of this talk. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.